If you remember from your class 9 knowledge, secant of a circle. What do you mean by secant of a circle? Any straight line that intersects the circle at 2 points is called a secant. So if you see, I have drawn this line. This is a secant of a circle. You draw this line of any length. Okay, this will be another secant. You draw this line. This will be another secant, right? All these, if you see, are intersecting the circle at 2 points, right? They're intersecting the circle at 2 points. So this line, which is of any length, which is drawn to intersect the circle at two distinct points, okay, is called a secant of a circle. Okay. Now, once we know the definition of secant, we now define what we call as a tangent of a circle. What do you mean by tangent of a circle? Now, see, secant intersect the circle at two distinct points, right? But a tangent is such a secant, such a straight line of any length that intersects the circle at only one point. Okay, this is called the point of contact of the tangent. Okay, this line L, which intersects the circle at only one point, intersects the circle at only one point. Okay, and if it intersects the circle at only one point, we say touches the circle. Whether we say touches the circle, that a straight line touches the circle, means it intersects the circle at only one point. Okay. Now, in certain textbooks, you will also find that they have defined the tangent in a little different way also. Not different, actually the same. See, if this point starts moving towards this point, if P starts moving towards Q, or you can also say Q moving towards P, then what will happen? This line will also start bending, right? If P start moving towards Q, this line will also start bending until the line becomes something like this here, right? So now this secant becomes a tangent. So as P moves towards Q, the line L becomes the tangent. Line L, or you can say secant L, becomes the tangent. Okay. But for and if you don't want to remember this way, it's okay, but just know that if any secant that touches a straight line at a particular point, that is intersects the circle at a distinct point, only one point, okay, that is called a tangent to a circle. And the point at which it intersects the circle, the one point that it intersects the circle, is called the point of contact of the tangent to the circle. Okay, so remember this word, very important word. Okay, if you take maths later on, this is going to pursue you. Okay, point of contact of the tangent to the circle. Okay, and now we come to the next concept, which is called how many tangents can we draw to a circle. Now the point is that tangents needs to be drawn to a circle from, can be drawn from a point inside the circle. Can it be drawn from inside the circle? It is not possible. See, this is a point P, and I will not be able to draw any tangent to this circle from this point because it is inside the circle, or we say point P lies in the interior of the circle. Okay, now if I consider another possibility where the point is on the circle, then only one tangent can be drawn. Okay, only one tangent can be drawn through a point on the circle. Okay, one and only one tangent. You can, if a point is on the circle, you cannot draw more than one tangent to the circle. Fine. Okay, and what is the third possibility? The third possibility is that you can draw tangents from a point that lies outside the circle. So if I take a point P here, then I can draw two tangents to the circle. One in this manner, from passing through this point P, and the other in this manner, which obviously will pass through the point P. Okay, so remember, two tangents or not more than two tangents can be drawn through an external point P. Okay, if the point P lies outside the circle, or we say the point P is the external point to the circle. Okay, so what have we discussed? If the point P lies inside the circle, no tangents can be drawn through a point P that lies in the interior of the circle. If the point P lies on the circle, then only one tangent can be drawn. Okay. And if the point P lies in the exterior of the circle, at most two tangents can be drawn, not more than two tangents. Right? So this is what you must know. So let's move to the next part. A theorem. A theorem which you have already done in class 8. Okay. The tangent and the radius are perpendicular to each other at the point of contact. Okay. If you see here, I have drawn a circle with the center O. So OP, this part is the radius, right? This line here is the line L is the tangent. And this is the point of contact, right? Now, according to this theorem, if I have any radius, and if I draw a tangent to the circle, then the point of contact of the tangent and the radius must be perpendicular at this point. That means this angle must be 90 degrees. Okay, so I have the tangent line L and I have the a line through the center or the radius. They must be perpendicular to each other. This must be 90 degrees. This angle has to be 90 degrees. So your conclusion is that OP must be perpendicular to L. Okay, the given here was circle with center O and tangent L at P. Okay, this was given to you. And you concluded that OP must be perpendicular to L. This is something that you have done back in your class 8, right? Okay. Moving on. A small problem here, the likes of which you have already done again in your class 8. Let us briefly discuss this problem and then we can move ahead. Calculate the length of the tangent AP drawn from an external point. So this P is your external point. Okay, diagram is not given. You have to draw the diagram. Calculate the length of the tangent AP drawn from an external point. So you take an external point P, distant 13 centimeter from O. That means distant 13 centimeter from O. That means this length is given to you as 13 centimeter of a circle of radius 5 centimeter. And you have drawn a tangent here, right? And the radius, what you do is that from the center to the point of contact, you draw a straight line and this becomes your radius, right? So now once you know these measurements, so you know the length of OP and you know the length of OA. Okay, you need to find out the length of the tangent. Now we shall use this theorem that we have said. Any radius is perpendicular to tangent. So this is your tangent and this is your radius. And point A is the point of contact. And you know that the radius and the tangent are perpendicular to each other at the point of contact. That means this angle must be 90 degrees. So what have we done? We have actually constructed a right angle here. When this angle is 90 degree, angle A is 90 degree, then triangle OAP becomes a right angle triangle in which OP is the hypotenuse, right? OP is the hypotenuse. Once we know this is the hypotenuse, then we can apply Pythagoras theorem here. This becomes your perpendicular, right? And this becomes your base. And you can apply your Pythagoras theorem to find out the length of the perpendicular. And this length of the perpendicular will be the length of the tangent AP. Okay. This kind of problem we have already discussed back in class 8. Moving on. Now we come to the converse of this theorem. Now, if you remember in the theorem that I told you, this converse was not there in your class 8. But in this theorem, I said if a tangent is given to you and that is where P is the point of contact of the tangent, and if you draw any line through the center, this angle must be 90 degrees. Now, what if I interchange these two? That is, see if this was given to you, and you can conclude this, right? That is what is meant by the converse, and that is what has been stated. So let's see what the converse of this theorem states. Converse of this theorem. The converse of this theorem states that the perpendicular to a tangent through its point of contact passes through the center of the circle. Always that if I have a tangent, that is a tangent is given to you, okay, and if I have any straight line, that passes through the point of contact. So if you see this line M, this passes through the point of contact, right? And is also perpendicular to the tangent. So it is given to you that this line L and M are perpendicular to each other and they pass through point of contact. Then your conclusion is that this line M must pass through the center of the circle. Now you understood the difference between the main theorem and the converse. In the main theorem, it was given that the line already passes through O. But here, it is already given to you that the lines are perpendicular. And now you concluded that it passes through the center O. Okay. So that is what the converse means. Converse was not there in class 8. So now we have discussed in class 10 what the converse of this theorem means. Okay. Next, a very important theorem here, that if two tangents are drawn from an external point to a circle, then the length of the tangents, then these are the conclusions. These three are the conclusions. Okay. In fact, these three can be classified as single theorems. Okay. Three theorems, three separate theorems, but I have clubbed them together. Okay. So let's see what this theorem means. If I have a point P here, and if I draw two tangents to the circle whose center is given to me. Okay. So this is given to you. So what is given? Center of the circle is given, and the external point from which two tangents are drawn to the circle, that is given, right? And you also know the point of contacts. Okay, A and B. So A and B, these two are the points of contact. This is also a point of contact. Okay, these 2 points of contact are given to you. Then what can you conclude? The first conclusion that you can make here is that the length of the tangents drawn from P must be equal, right? That is, these two lengths must be equal. PA is equal to PB. These two lengths must be equal. So if you see, the first conclusion is that PA is equal to PB. The next conclusion is that the tangents subtend equal angle at the center of the circle. If you see, the angle subtended by this tangent with point of contact A subtends an angle at the center, this. Subtends an angle at the center, this. Okay. And the other tangent subtends this angle. These two angles must be equal, right? This is another conclusion. The next conclusion is that the tangents must be equally inclined to the line joining the center of the circle to the point of contact. So the line joining the point of contact to the center is this line, and the tangents must be equally inclined. That means these two angles must be. So I have three conclusions here. What are the three conclusions? The three conclusions are, again repeating here, that the length of the tangents must be equal. This length must be equal to this length. The next conclusion is that this angle must be equal to this angle. And the third conclusion is that these two angles must be equal. So if any two tangents are given to a circle from an external point where you know the points of contact and you know the center, then these three are the conclusions that you can make. Fine? Okay. So once we have discussed this theorem, let's do a problem based on this theorem. Here, this problem. If you see in this figure, ABC is a triangle ABC is circumscribed in the circle. Okay. Now, what do you mean by circumscribe? Circumscribe, surrounding the circle. Okay. You need to find out the value of x. Right. So how will you find out? Let's see how to begin. First of all, what you must notice is that this length here and this length here, these two lines are nothing but tangents drawn to the circle from the point B, right? These two, PB and RB, these two are tangents drawn to the circle from the point B. And you know that the length of the tangents drawn from an external point to a circle must be equal. So therefore, if this length is 6 centimeter, this length must also be 6 centimeter, right? So PB must be equal to BR, equal to 6. So part of X we have already got. The only thing remains is we have to find out this. And once we are able to find out this length, we just add them and we'll get the value of X. So let's see how to find. So this much we have got as 6 centimeter. Next, what you see is that this AP and this AQ are tangents that are drawn from the point A to the circle, right? If these two are tangents drawn to the circle from the point A, then their lengths must be equal according to our theorem. So if this length is 4 centimeter, this length must also be 4 centimeter till this point, right? Because why? The reason is because the length of the tangents drawn to a circle from an external point are equal. So this is 4 centimeter. Now, once we get this as 4 centimeter, what is the remaining length here? This entire length EC, if you see, is given as 12 centimeter. So this length here is 12 minus 4, which is equal to 8 centimeter. Now this, if you see, this length here is nothing but this CQ, this length that we have found out, 8 centimeter. This is the length of the tangent drawn from C, right? Also, if you see CR, this length is also a length of the tangent drawn from the point C. They must be equal. So if this is 8 centimeter, this is also 8 centimeter. And hence, what is the value of X? 8 plus 6 is equal to 14 centimeter, right? No question? Okay. Let's proceed with the next problem then. Okay, another problem. In the figure given below, O is the center of the circle. Tangents to the circle at A and B meet at C. So I have a tangents drawn through A and through B. So A and B are nothing but points of contact. Okay. Meet at C. That means whether you say tangents drawn from A and B meet at C, or whether you say tangents drawn from an external point C with points of contact to the circle A and B. It's the same thing, synonymous. Okay. So A and B are nothing but points of contact. Also given is angle ACO is 30 degrees. So you see this is already marked in the figure, 30 degrees. Okay. Now let's look at this figure. You need to find here angle BCO. So you need to find this angle, which is a cakewalk, because you know that this angle must also be 30 degree, because this angle is 30 degree. Why should it be 30 degree? Because the contour statement is that the tangents drawn to a circle from an external point are equally inclined to the line joining the center and the point, to the line joining the center and the external point, right? That is the statement. So this angle must also be 30 degrees. So first question is answered. BCO is 30 degrees. Next, angle AOB. So angle AOB is this angle here. Okay. So how do I find out this angle? See, first of all, once I have found out this angle to be 30 degree, this angle must be 90 degree, because OA is the radius and AC is the tangent, and you know radius and tangent must be perpendicular to each other at the point of contact, right? Now once we know this to be 90 degree, you can, if you consider this triangle here, OAC, in this triangle you know two angles, 90 and 30. That means what should be the third angle? 180 minus 90 minus 30, which must be 60 degree, right? So you know this angle to be 60 degree. And what is the theorem that you know? You know that the tangents to a circle drawn from an external point subtend equal angle at the center of the circle. So that means if this angle is 60 degree, this angle must also be 60 degree. And therefore, what is this entire angle? 120 degree. So this entire angle here is 120 degree. Okay. So that completes the second part of this question also. Next question is APB. So how do you find out APB? If you see here, this 120 degree angle is the angle subtended by this arc AB at the center of the circle, right? And angle subtended by the same arc AB on the remaining part of the circle is this. And you know that the angle subtended by an arc at the center is double the angle subtended by it on the remaining part of the circle. So therefore, this angle must be 120 by 2, which must be 60 degree. And that completes the third part also. Okay, fine. So that completes this question. Okay, now we start with the next part, which is touching circles. What do you mean by uh, the two circles touching each other? What does it mean? Okay, now two circles can intersect each other, right? When can two circles touch each other? If you remember, the word touch, as I told you, means only one point of intersection. If a tangent touches a circle, it means it has only one, it intersects the circle at only one point, right? Similarly, if two circles intersect each other, they can intersect each other at 2 points this way, right? These A and B are the points of intersection, right? If, however, the circles intersect each other at 1 point, okay, that means if these two are one and single point, that means we say that the circles touch each other. How do they touch each other? How can circles intersect each other at 1 point? This is the way they can touch each other, in these two ways. First is, if you see these two circles touch each other externally at P. Okay, so these two circles touch each other externally because both circles are outside each other. And if you see in the second diagram, these two circles touch each other internally. Why do they touch each other internally? Because one circle is inside the other circle, right? And this point here is called the point of contact of the two circles. Okay, just as in case of tangents, we have the point of contact when the straight line touches the circle, we have a point of contact. Similarly, for circles touching each other also, we have a point of contact. That is the point, the single point at which they intersect is called the point of contact of the two circles. Okay. Now, from these two circles, from this point of contact, if we are to draw a straight line through this point of contact, right, then this is called the common tangent of the two triangles. This is called the common tangent of the two triangles. Similarly, this line, if I draw through the point where the two circles intersect, this will be called the common tangent of the two circles, because this tangent is belongs to the circle with center A also, and this is also a tangent to the circle with center B. Similarly, this the in the second one in this figure also, that this straight line is a tangent to the circle with center A and the circle with center B. Okay, this is what we mean by common trend, and point of contact I have already told you. Now is a concept of common tangents. Okay, not that this concept is not too important, but still just for mention, and you can go through this, that there are two kinds of common tangent. If you have two circles, then you can have two types of common tangents. Common tangent means tangent to both the circles. For example, in this case, when the circles touch each other, this is a common tangent, this straight line. This is a common tangent. And similarly, this is also a common tangent. This is the case of common tangent when the circles touch each other. What is the case of common tangent when the circles don't touch each other or do not intersect each other? This is the case. So if you see, if you have tangents drawn in this manner for two circles which do not touch each other nor intersect each other, then this type of tangent is called direct common tangent. Because why common? Because these two lines also belong to the these two are actually lines common to the both the circles. Okay. Similarly, you can also have transverse common tangent. What does a transverse common tangent look like? This is how a transverse common tangent looks like. Okay, so you just draw a straight line here such that it touches this circle here and touches this circle here, and here you draw a straight line like this such that It touches both the circles. Such a tangent, when you're drawing tangents in this way, such tangents are called transverse common tangents to the two circles. Okay. So just know the definition for the time being and that will work. Okay. Again, the last theorem that I'm going to discuss for today is this. If two circles touch each other, then the point of contact lies on the straight line joining the centers. Now, what does this mean? So given here, if you see in the first, I have two circles that touch each other externally, external touching, in which P is the point of contact, and this is internal touching, in which again P is the point of contact. Okay. This theorem states that if two circles are given which touch each other at the point P, okay, whether it be internal or external, and if you draw a straight line joining the centers of the circle, this will necessarily pass through P. Okay. You cannot have, this theorem states that you cannot have a straight line like this which does not pass through P. It will always pass through P. Whenever you have two circles touching each other and you draw a straight line joining the centers, this will always pass through this point, the point of contact, whether it is internal or external. Similarly, if you have these two, A and B, if you join these two, and now if you produce this straight line will always pass through this P. Okay. It is not possible that if you draw a straight line like this and it will not pass through P. No. Okay. This straight line will necessarily pass through the point of contact. Always. So whenever you have two circles that touch each other, whether internally or externally, the line joining the centers of the two circles will always pass through the point of contact. Okay. Similarly, A and B, this will always pass through the point of contact. It cannot pass through, it cannot just skip the point of contact. It will always pass through the point of contact. So you can say A, P and B are on the same straight line. A, P and B must be on the same straight line. Now you might say that what is so new about it? It has to pass through. No, it is not necessarily so. Okay, you have to prove this theorem that if I have a straight line joining, passing through, joining the center of the circle, it will pass through P or not. There's a proof that exists. Okay, so it is not common sense. You have a geometric proof for this. Fine. So I'll stop here.